Ever notice how a car's wiper glides or scissors snip with ease? That's the magic of mechanisms, systems of levers and joints that turn one type of motion into another. These mechanisms are everywhere, from toys to cranes, quietly powering our world. But what if the parts themselves could move and change shape, acting as both bone and muscle? Enter smart materials, substances that react to electricity, heat, or magnetism. Today, we'll explore how combining classic linkages with smart materials is revolutionizing engineering, from airplanes to medical devices. Let's dive in and see how the future of machines is being built right now. Before we leap into the future, let's understand the basics. Mechanical linkages are the skeletons of machines. A linkage is a set of rigid bars, links, joined by pivots, controlling and transforming motion. The 4-bar linkage is a classic 4 links, 4 pivots, 1 fixed frame, 1 input, and 2 that transmit motion. You'll find it in car suspensions and oil pump jacks, turning simple input into complex, useful movement. The slider crank linkage is another star converting straight-line piston motion into rotation. Think car engines and steam locomotives. These systems are reliable and powerful, perfected over centuries. Gears, cams, and motors drive them, but the links themselves are always rigid, just the bones. To move, they need an external muscle, a motor, engine, or hydraulic cylinder. But what if the bones could move themselves? Imagine a linkage where the structure is also the source of motion. That's the leap smart materials make possible. Instead of adding more parts, we can design machines where the links themselves flex, contract, or twist on command. This shift is transforming how engineers think about motion and design. The future isn't just about assembling parts. It's about inventing new kinds of parts altogether. Let's see how these muscles work. Get ready to meet the materials that are changing everything. Smart materials are the game changers. Substances that respond to heat, electricity, or magnetism by changing shape or stiffness. Shape memory alloys, SMAs, like nickel titanium, remember their shape, bend them cold, heat them up, and they snap back. Eyeglass frames use this trick. Piezoelectric materials generate electricity when squeezed, or change shape when electrified. Think of the spark in a gas grill igniter. Magnet or heological, MR fluids are oils with iron particles. Add a magnetic field, and they stiffen instantly, used in advanced car suspensions. These materials act like living tissue, reacting, adapting, and powering movement without bulky motors. They're already in products you use, often unnoticed. Imagine machines where the muscle is built right into the structure. That's the promise of smart materials, motion, precision, and adaptability, all in one. The next step? Combining these muscles with classic linkages. Let's see what happens when we do. What if a linkage's moving part was made from a smart material? Now, the link itself becomes the actuator. Replace a steel link with an SMA wire. Apply current. It contracts, and the whole mechanism moves. No gears or motors needed. This fusion of structure and function means lighter, simpler, and more reliable machines. In aerospace, every gram counts. Smart linkages cut weight and complexity. Piezoelectric actuators can make tiny, rapid adjustments, perfect for cameras or medical devices. MR fluids let robotic arms move fast, then stop smoothly with no vibration. We're not just pushing and pulling bars anymore. We're programming materials to move, bend, and stiffen on demand. Smart linkages open up new motions and designs that were impossible before. Fewer parts mean fewer failures and easier maintenance. The result? Machines that are more efficient, precise, and adaptable. This is the new frontier of motion. How do engineers draw these new machines? Traditional linkages use solid lines for links, circles for pivots, and symbols for motors. For smart linkages, we need new notations. Use wavy or shaded lines to show a link made from a smart material, like an SMA. Add notes specifying the material and its behavior, such as SMA link, NIT alloy. Show both the unactivated and activated states, with dimensions for each. Indicate activation conditions, heats above 90 degrees, or 5 VDC. Use dashed lines to overlay the moved position, making the range of motion clear. Call out control systems, wires for piezo actuators, magnets for MR fluids. The goal clear, simple communication so anyone can build or repair the design. These new drawing conventions are spreading fast as smart materials become more common. The language of engineering is evolving to keep up with the technology. With the right sketch, a revolutionary idea can travel the world. Next, let's see these ideas in action. In aerospace, weight and reliability are everything. Smart materials are transforming airplane wings. Embedding SMA wires or piezo patches lets wings morph shape like a bird's without heavy hydraulics. This aerodynamic shaping means perfect lift for takeoff, sleek efficiency for cruising, and fewer moving parts to fail. Helicopter blades can now change shape in real time, reducing noise and vibration. Satellites use SMA hinges to unfold solar panels in space. No motors, just sunlight and smart design. The result: lighter, simpler, and more elegant machines. Smart linkages are making flight more efficient and reliable. The sky is no longer the limit. Smart linkages are revolutionizing robotics and medicine. Soft robots, powered by smart materials, can bend and squeeze through tight spaces, safe to work alongside humans. Grippers with SMA wires or fluidic channels gently handle delicate objects, adjusting grip in real time. In medicine, smart catheters with embedded wires let doctors steer through blood vessels with precision. Prosthetic hands use smart actuators for lighter, more natural movement. MR fluid braces and exoskeletons stay flexible, but stiffen instantly to prevent injury. These advances mean safer surgeries, better assistive devices, and more human-centered technology. Smart materials bring machines closer to the adaptability of living things. The future of care and collaboration is soft, precise, and responsive. Smart linkages aren't just an upgrade, they're a new way of thinking. By combining structure, sensing, and actuation in one part, we get simpler, lighter, and more reliable machines. Fewer parts mean lower costs and easier maintenance. Machines can now sense and adapt to their environment. Wings that respond to turbulence, arms that adjust their grip, devices that navigate the body. This is functional integration, building systems that behave more like living organisms. It's a field where mechanics, materials science, and electronics meet. The engineers who master these skills will shape the next generation of technology. The future belongs to those who can imagine and build what's never been done before. We've journeyed from simple linkages to smart materials that move and adapt. This revolution is happening now, and it's just beginning. Imagine buildings that flex in earthquakes, clothes that adjust to temperature, or energy devices that adapt to the sun and wind. You don't need a lab to start. Experiment with linkages. Try SMA kits and let curiosity lead you. Ask questions, take things apart, and dream up new solutions. The future is built by those who learn, experiment, and create. By mastering the basics and daring to innovate, you can help shape a smarter world. The next breakthrough could start with your curiosity. Go for it.